Okay, so I'm going to tackle lesson set. I don't know if it's 25 or 26. I'll find out later. This is all the new material for the second half of the term. I don't want to say all. I mean, I really don't know. See how things go. But it's what we're hoping to cover and cover well. And the only way that we can begin that process is to begin that process, start a conversation. So in this video, and it may seem overwhelming again, just like the beginning of the term did. We're going to be doing a rational function, graphing a rational function. I'll write one here in a moment. Let's go y equals 6 over x minus 3. So we'll graph that and I'll point out what I see. And then you'll just keep hearing about what I see and then what your peer group sees if people start doing it correctly. We'll get those conversations started. We're going to do a unit circle problem, sine of 5 pi over 3. And if you haven't looked at the intro to the unit circle, you might get lost on that. And if you haven't looked at what is a radian, then that concept may take a while, if at all. A lot of people finish a trig course and don't know what a radian is. And if you don't know what a radian is, I'm not sure you understand what trig is. So that's going to take some time. We're going to solve a trig equation, graph a trig function, graph a cubic. Let's start graphing cubics, which is just as easy as graphing a quadratic. It's just one more step. Maybe 2 steps if we want to put in some more data, and we will. Local max and mins, that's what I mean by 2 steps. We'll immediately know if a cubic has local max and mins, but then again, we should be able to find them easily, just as easy as finding the roots of a quadratic, given a picture. We're going to do another rational function. It gives you a chance to recall. Another 20 minutes after doing this, or 25 minutes, we do another one, which means you got to try to recall some things. And that's what math's all about. Recall, understanding what's being asked and how to work with it. Recall. Okay. How do you improve recall? You repeat things. How do you improve recall? Okay, enough of that. All right. So we're going to look at the limits associated with the rational function once we get a little bit of discussion going. We'll do a variation problem, at least 1, maybe 2, and that should have been covered in Algebra 1, so it should be just review. I have a feeling it won't be. Rules of logs, we've already been starting the rules of logs. Now we're going to officially start writing with the rules of logs. We're also going to look at the rules of exponents. You know, how you exponentially either add exponents, subtract exponents, or multiply exponents. Oh, I'm sorry, that was redundant of me. That's exactly what the rules of logs are. My fault. Okay, we're going to look at mixture problems. Again, those should have been done in Algebra 1. And first derivative. Let me get the screen a little brighter so I can see a little better. We're going to do our first derivative with a quadratic, get the conversation started. I'm a big fan of giving some of the more difficult concepts air earlier in a student's career. I saw a YouTube video of a MIT grad. I didn't get to see much of the video, but the caption was, and I looked at maybe the first 30, 40 seconds, teaching calculus to 5th graders. Oh, I was happy to see that. Absolutely happy to see that, because all of the derivatives really come from geometric pictures, and people understand how to draw a square. People understand how to draw a cube, which means we have a chance to see what's going on rather than just work with symbols that maybe lack meaning. Okay, so let's have at it. Let me get this erased. Let me tell you what I see here. If I was looking at that, and I was asked to graph it, I would take the following steps. First thing I'd do, I'd get a y-intercept, a frame of reference. Okay, we practiced y-intercepts. I hope you already know what that one is. I put in a 0. I get -2. Now look at the x-intercepts. X-intercepts are when y equals 0. So we have to look at 6x minus 3 equals 0, which means that 6 is equal to 0 times x minus 3. And that means 6 is equal to 0 because division becomes multiplication, and 6 equals 0. Okay, I didn't know that. I guess this doesn't have an x-intercept. No, I guess maybe I could spot that the next time more easily. As in, fractions are numerator and denominator, and I think 0 only comes from when the numerator is 0. Huh, I don't think I can make 6, 0. If you can think of a way to do it, please get in touch. Okay, so there's not going to be anything that crosses the x-axis here. And I know this is a fraction, and I know fractions can be positive or negative. And I think it's negative when numbers are less than 3. I think we're going to get negative answers, negative y values for x. Well, what happens at 3? I get 6 divided by 0, which is, I think, undefined. So I guess I got some asymptotic behavior here. And, if there's nothing when x is 0, inquiring minds want to know what happens when x is 0.01. Well, I think that goes into 6 lots of times. So I think a number like 3.01 is going to give me a calculation like that, and I think things are going way up. Notice I'm working with numbers. If you're not plugging numbers into these functions, you're going to have a real hard time picking up quickly what these graphs look like. So may I encourage you to put numbers in? And numbers can be big. And big numbers are what we refer to as end behavior. End behavior. And if I want to understand the end behavior of this graph, then I have to get started with a number. Well, I don't know what's a big number for you, but graphing calculators usually go from -10 to 10. So why don't we pick 100? Put 100 in here. And I get 6/97. And I don't know what integer that's closest to. Actually, I do. It's close to 0. So I'm really going from infinity to 0. And why don't we nail one more number here? What would be a nice number besides 3? Maybe 4. I think 4 gets me 6. I don't think I have to show you that. I think you can put 4 in and figure that out for yourself. Then I think I get a sign change at 3, because if I put 2 in, I get -6. So 2, might as well plot it. 2 gets me -6. Wow, that's got a curvature to it. Yeah, well, what would happen if I did 2.999999999999999? Well, that's -0.01 into 6. Yeah, a lot of negative times. And I think we're heading to 0 over here as well. When I put -1,000,000 in, I get -6/1,000,000, or as many zeros as I want. Keep doing that forever. That's what limits are about. So there's your graph. All right, now we're looking at the sine of 5 pi over 3, and our goal is 2 months from now to be able to say -√3/2. All right, let's get rid of this. And if you're looking at the intro to unit circle, then you already know that you're looking at a 30, 60, 90-degree triangle. And if you haven't looked at that, I apologize to you right now, because this won't make much sense. Pi, top half of the circle, broken up into 3 parts. Good drawings get good answers. If there's 3 parts in the top half of the circle, then there's 3 parts in the bottom half. We start our walk around the circle from 0 pi over 3. I haven't walked any arch distance. Then I walk my first arch distance, which is about 1.05 radius lengths. Radius lengths. About, I said. The exact amount is pi over 3. How did I get a 1? I did 3.14 divided by 3, and I just approximated to give you a sense of the radius is 1. This distance is a little more than 1. Not much. Now, once we get to a place on the circumference, we drop a perpendicular or bring one up to the x-axis. We now have 90 degrees. Pi divided by 3 is equivalent to 180 degrees divided by 3, right? The top half of the circle is 180 degrees, and I broke it up into 3 parts. So that's a 60-degree angle. And in the intro to the unit circle, we broke that down using the equilateral triangle. That's a half. That's √3/2, and that's 1. But I'm not at pi over 3. No, I'm at not 2 pi over 3, not 120 degrees, not 3 pi over 3, not 180, not even 4 pi over 3, not 240 degrees. No, I didn't go 240 degrees. I actually went 300 degrees, 5 pi over 3. 5 times 180 degrees divided by 3. I think I would divide by 3 first and get 5 chunks of 60. 1, 2, 3, 4, 5. What do I do when I'm there? I highlight that triangle, not the others. And what do? I draw a perpendicular. I know the hypotenuse is 1. It never changes signs. I know the cosine is a half. And now I know the answer to this is negative root 3 over 2. I don't know if I said negative or positive at the beginning, but right now that's negative root 3 over 2. And I've asked you to memorize it. And I know most people still haven't, even though I asked it on day 1 of the semester. Negative 0.87. Bet you half the class that knows that now. I want you all to know that. So what's the cosine of negative 19 pi over 3? Negative 18 pi over 3 is 6 pi. I'm going one more. I think it's a half. Let's find out. Because I don't trust my mental math anymore when I'm talking to you. But I got a circle. I want to break it up into thirds again, but this time I'm going counterclockwise. I'm going, remember, sinusoids, we've been doing this, right? But there's another side to them. Okay, so we're going backwards now on the circumference of the circle. Once around, starting at 0 pi over 3, once around is negative 6 pi over 3. Then we got negative 12 pi over 3, 2 revolutions, negative 18 pi over 3, 3 revolutions, negative 19 pi over 3 is coterminal to the last triangle we drew. So we're in a coordinate system. I'm still here. And that's a half. So I don't know if I said that or not. What was I doing? Was I doing sine the last time I said something? I don't know. But this is a half. All right, now that I'm doing it out. Again, that's minus root 3 over 2, and that's 1. Same triangle. But we just talked about going in the other direction around the circumference. All right, so I might have said something wrong there. Yasser will pick it up on there for me. I appreciate that. Because it takes time to do these. Takes time to teach class. Takes time to write these worksheets. Takes a lot of time. What I hope doesn't take time is being able to look at that and go, oh, I think I got all the odd pi over 6s. So this is just unit circle work. And so what's our first step? 1 divided by 4 is 1/4. Taking the square root of a fourth, which is plus minus a half. And so therefore the sine of what angle? X stands for an angle. Notice I'm trying to highlight all the foundational vocabulary. Again, I don't expect you to follow this 100%. Just moving in the right direction is good enough for our start. We pick up on it again, another lesson set tomorrow, another one on day after that, another one on a day after that. And by the 4th time you hear this, some of it'll make some sense. Keep the coffee going. So we looked at in the intro to the unit circle. If we put that triangle on its side, then half the hypotenuse comes from the 30-degree triangle, and that's going to be on your SATs. So a 30-degree or pi over 6 gets me the half. So let's draw the triangle, and let's draw 1/2. That's a height of 0. That's a height of 1. Halfway. Good drawings get good answers. That's about halfway. Here's the origin. Does it look like that 30, 60, 90 on its side? Does it look like that 30? That's a reference angle of 30 degrees. It's really 150 degrees to here. Does it look like that's halfway up to 1? Again, here, halfway, a little bow tie, Charlie. Oh, yeah, or negative 1/2, we said, right? So this is chunks of 6. So that's pi over 6. 1, 2, 3, 4, 5 pi over 6. 7 pi over 6. There's all the odd, pi over 6. 11 pi over 6. Okay, so where on the sine curve am I a half? Pi over 6. 5 pi over 6. 7 pi over 6. 11 pi over 6. One period of the sine function captures all those snapshots. All right. I'm not worried about talking fast right now because I don't expect you to pick it up in one day. So the sine function, we're going to graph it. What's the sine function look like? Well, if I start here, in the first 90 degrees, I go up to 1. Woo! First 90 degrees. There. Then in the next 90, I come back to the midline. The next 90, I come back to the midline. Okay, so that's 90 degrees, 180 degrees. We'll be doing radians enough. I can do degrees right now. 270 brings me to a minimum of -1. 270. The altitude is -1, and then it comes back up to 1. Now, we're going to take that general theme, which is the sine function at a given angle. Here's the graphing form. The multiplier in this case was 1. I'm only going up 1 and down 1 with the sine function and the cosine function. So how's this different? Well, now my radius isn't 1 anymore. My radius is actually 10. 10 times that. So I'm going up and down 10. And I'm not at 0 anymore, I'm at 7. So this is a height of 7. So that's 17. And then down 10, -3. Other teachers are going to use shifting language. The sine function has shifted. I think it's measuring change from 0, but I am slowing down that change, right? Because 30 degrees divided by 2 is only 15. I wouldn't get a half anymore, right? Unless I picked a 60-degree angle. So this thing in the language of transformation is stretching. All right, I want you to hear those terms because that's what you're going to hear in another class. I'm suggesting you just treat this. Used to start at 0, it still does, right? 0 divided by 2 is 0, but we end at 2 pi. We want the sine of 2 pi, the end of the revolution, go Che. Well, I think that happens at 4 pi. So how are we going to find where something starts and where something ends? The sine function has a parentheses, and we want that parentheses to equal 0. That's where you start. You walk around the circle, and we want that parentheses to equal 2 pi. We'll find shortcuts as we go along, but whatever's in the parentheses, set it to 0. You're going to get your start. Whatever's in the parentheses, set it to 2 pi. And in this case, that becomes 4 pi, brings us back to 7 as a height, 17 as a max, -3 as a min. I'm off screen here, but hopefully you see that I wrote 4 pi here, brings me back to 7, which means that 2 pi, we got a lot of symmetry here, and pi should get me, 17? Pi should get me 17. Well, let's look at that one. Let's put pi in. So where's pi? Pi is over here, but pi divided by 2 is there. That's a max. That height is a max. It's 10. And 10 plus 7, 17. All right, so that's enough of that one. Now we're going to look at, I was going to graph a cosine curve, but I think I'll pass on that. You got enough on your plate. So let's look at graphing. Yeah, I don't have, I need Rene the card. I don't have Rene. So we'll do that instead. So 2x cubed, kind of looking at it sideways there. Okay, hopefully that's good enough. So I want to put that in graphing form. Well, one thing I definitely know is -5, 0, -5. And I also know that I'm going up at 10 to 1. We'll learn that. Not too much distant future here. So I know this is going up, and I know eventually it keeps going up. So the question is, does this bend? Oh, I know, I changed this. I was playing with this in class. So I want to do -10x. I want to get the local max and mins involved. And I don't think if it was +10, I get that. So I'm going down at 10 to 1. And therefore, I know that this graph hinges. It's going to do this. And I want that location. We've already studied that in class. That's minus b over 3a. So minus b, 6 divided by 3 times 2 is 6. I picked a nice, easy number. And I know I'm going to be going down faster than 10 to 1 because at the point of inflection, I'm decreasing fastest right here in this model. And that's going to happen here as well. So I've got a graph that's going to look like this. Okay. And it's going to have point of inflection there. I don't know how high, what the y value is. I know those x values immediately once I find the point of inflection and the rate of change there. All right. So the rate of change at the point of inflection is a little c minus 3a h squared. cubics come in the form of ax cubed plus bx squared plus cx plus d. All right, and that's all I have to do. And this is hk, just like hk, the most important place on a quadratic we refer to as hk. I'm referring to hk here because I don't think cubics in graphing form are in many. I haven't seen it. I haven't seen it on the internet. I haven't seen it in textbooks. So I doubt this is the first time it's been written, but it doesn't seem to be out there. So we can get this really easily with calc too. But this was done without calc. All right, so let's have at it. Do I have the eraser? No, of course not. All right, so we found out that 1 is the x value. So we now know h is 1. H is 1. Now we need to know what goes with 1. So we got 2 minus 6. Notice the 3-to-1 ratio. In the quadratic, it's 2-to-1 in opposite. Here it's 3-to-1 in opposite. Heck of a coincidence. Minus 10 minus 5. So that looks like it's 19, negative 19. So I'm actually almost ready to put this in graphing form. So C in this case is minus 10. That's the C term. Minus 3. A is given. There's nothing new to learn there. That's a 2. And H, well, is minus B over 3A any harder than minus B over 2A? No, same level of difficulty. In this case, it's 1 squared. So we're going down at 16 to 1. We now have this in graphing form. So the graphing form for this is as follows. Take what's given. So I'll put it here because I'm running out of room. 2x minus 1 cubed minus 16, x minus 1 minus 19. That's the graphing form for a cubic. And for those of you chiming in from a calculus class, that's the equation of the line tangent to the point of inflection. And without realizing it, you could have just done this and you'd have the graphing form for a cubic. I know, it's hiding there, isn't it? Yeah. All right, so what's this x value? That x value starts just like the problems we've been doing here. We've been looking at 8, 3, a equals 2, and writing the roots. Some people are having trouble seeing this as imaginary roots because that does not intersect the height of y equals 0. I'm seeing people write x equals 8 plus or minus the square root of 3 halves, imaginary. Half the class is doing that in 5 seconds or less. This is the same level of difficulty. Okay, so the max and mins, local max, if they exist, and if they exist, the slope and the a term have to have the same sign. They both have to be positive or they both have to be negative, or you don't get local maxes and mins. That's immediate. All right, so it comes from that slope. That slope comes from the minus b over 3a, which I'm going to call h, plus minus. Oh, yeah, we have one that's 1 minus, and we got one that's 1 plus. That shouldn't look foreign to you. I don't know if I want to use that word. Shouldn't look like you've seen that for the first time. All right, square root of opposite of negative 16, positive 16, divided by 3 times a. And a in this case is 2. So those are those x values. This one is 1 minus the square root of 16 over 3, and this one is 1 plus the square root of 16 over 3. Those are the x values for the local min and the local max. Okay, that's a mouthful right now, but a week or two from now, we're going to be able to do that quickly and easily. And I've had 6th graders put cubics in graphing form, so I don't think that should be any problem. All right, so what are the checklists? Just going to do this real quick. I can immediately see 6, negative 4, minus 1.5. 0 gets me minus 1.5. I can immediately see 4 is an x asymptote. I can see that this goes to 2 to 1 on the right and left. How do I know that? Because if you put a billion in here, you have 2 billion plus 6 over a billion minus 4. And if you're a billionaire, I don't think you care about $6 or $4 or who knows what you care about. That's getting into politics. Can't do that. No, y equals 2, y equals 2. Some people out there are very giving. Some people are not. So I encourage anybody hearing this that's a billionaire, please be giving. A lot of people out there need your help. All right, I better be quiet. 2. So I now know that goes there. I know that this thing ends up here. So I've got an x-intercept that's going to be negative. So what makes 0 here? I've got to go look. Oh, -3. Yeah. Now I can answer some questions. What's the limit as f of x goes to infinity? As I head to bigger and bigger and bigger numbers, I'm getting closer and closer to 2. If I come in from 4 to the right, oh, that's coming in from 10, 9, 8, 7, 6, 5, 4.5, 4.01. Using numbers. Put it into that x, do the math. I know this is near 10. And this is going to be 10 divided by 0.01. Now that goes to infinity. And if I come in from the other side, then it's 3.9999999. All right, so that's going to negative infinity. And what you'll learn is if you're not going to the same place, you're not trending to the same place, then we say that limit does not exist. First time you're hearing this stuff, relax. Variation. 3 types of variation we're going to look at: direct, inverse, and joint. We'll worry about joint later. As in, maybe I'll have you write one. All right, so direct variation from your Algebra 1 class. Y equals K times X. That's called the constant of proportionality. We got to find that first by substituting 8 for X. 8 times K equals a Y value of 24. We've now figured out that K is 3. All right, well, what if I change X to 10? Well, 10 times K, I know what K is now. It's 3. Oh, I guess I can figure that out. Say it's 30. Okay, inverse variation. Inverse variation is Y equals K over X. Of course, I just erased 8 gets us 24. So I got to find the constant of proportionality. My Y value is 24. And that's equal to some number divided by 8. Oh, I got a big number here. 160, 192. So K equals 192. So what if I divide that by 4? Let's change X to 4. Well, I should be able to say that Y is equal to what? 38? No. 4 into 19, 48. 4 into 19, 16, 4, 32. Yes, 48. So what happened? My X's went smaller. My Y's went bigger. We call that inverse. Joint variation is things like statements like Y varies directly as X squared and inversely as the square root of Z. We just add more variables, learn the language. I don't think that's going to be too hard. The ln of 10/3, I'm going to change that problem. I think I want to do 20 thirds. Yes, I'd rather do 24. I think this is a better example. Let me give you that example. All right, because we're going to do the rules of logarithms. So what we've been doing in class is writing 24 in E notation, which is 2 to the 3 times 3. 8 times 3 is 24. Okay, so rules of logarithms. I could write that here right now. 2 times 3, 2 cubed times 3. I could do that. Now it's ln, so we got to work with E. So we change this to e to the 0.7 cubed times e to the 1.1. It's approximation, right? So now I change this to the ln of e to the 0.7 cubed times e to the 1.1, and I need brackets around that. Thank you, Professor Flynn. Okay, I think I was improperly writing this for many years, unfortunately. I wish I could retract. Not a big mistake. Other people didn't catch up on it either, but Professor Flynn did. All right, so what's this become now? Well, I have rules of exponents. I'm multiplying 3 times 0.7. ln only looks at the exponential activity. That's all it looks at. So I think that's 2.1. And I can show that as, All right, I'm going to make the jump. 3 ln of 2. I'm multiplying 3 times 0.7, which is the ln of 2, and then I'm adding 1.1. Okay, so this 3 could have actually gone inside the parentheses to be the ln of 8. All right, so if the 3 were here, I'm permitted to do that. They are the same answer. That's still 2.1. And if I'm adding 1.1, I'm adding the ln of 3. And I hope you can see one of our first steps for the rules of logarithms. 8 times 3, where we started here, 24. Okay, so what's one of the rules of logarithms? Multiplication. Multiplication, 8 times 3 can be expressed exponentially as an addition of exponents. All right, m squared times m cubed, we write as m to the 2 plus 3. That multiplication implied addition of the exponents, provided the bases are the same. And that's what we're going to be studying in the second half. The 3 rules of exponential activity. When you multiply, you add exponents. When you subtract, you divide. And when you do power to power, you multiply. And we'll be expanding on that conversation in the weeks ahead. Just getting the conversation started. So can you tell me what the ln of 10/3 is? I think it's the ln of 5 plus the ln of 2 minus the ln of 3. Let's find out. 10 e to the, let's do 10 as 2 times 5 divided by 3, and let's change that into e to the 0.7 times e to the 1.6 over e to the 1.1. Well, what are you going to do with the exponents? You're going to add 0.7 and 1.6, which is the ln of 5 plus the ln of 2. And then you're going to subtract 1.1, which is the ln of 3. Conversation started. Running out of ink. Go figure. Not doing this one again. Forgive me, but I am going to take a moment and change cartridges. All right, back again. Almost done. Almost done. Hard to get started up and running with a lot of topics, but as we chip away at them, we can concentrate on the more difficult ones as we move along. All right, this is not new. All right, let me move the desk a little bit. I think I'll bring Renee the card up to the 3rd floor here the next time. All right, I'm going to write this as a sine and a cosine function. The cosine function maxes at x equals 0 for an angle. Straight across, the hypotenuse and the width are the same. There's no height. The sine function maxes at pi over 2. Not saying anything that isn't in previous lesson sets. So let's just start this. I've got to turn 1800 into pi over 2. And then I got 1, 2 pi, 3 pi. 3 pi later, 1907 has to be 3 pi over 2. Pi over 2, excuse me, plus 3 pi. And that's all I really need is the 3 pi. All right, so what is this one? This one is I'm starting at 30, going up 20 to get to 50. I'm going to do it as a sine function. I know I've got 3 pi units of change. 1.5 revolutions takes 107 years. Good, I'm counting by 100 better now. Made a mistake in a previous video. I got to make 1800 equal pi over 2. Just a linear function. Excuse me. X minus 1800. Plus pi over 2. A lot of you are getting that right now. So what is it as a cosine? Well, I just got to realize that 1800, I've got to make a 0. 0 degrees. I'll leave it as degrees. It's also 0 circumference distance. No arc distance. All right, and that's the one I'm going to use. That's an angle. All right, so it's 30 plus 20 cosine 3 pi over 107 x minus 1800. And I'll write 0 here. It's a different angle. Obviously wouldn't have to write that. That's the one that's usually done in the textbooks. But I think people have a harder time thinking about maximum width than maximum height. So that's why I'm teaching it this way, for starters. But if you take a look at this, it only looks like the cosine and the sine function are 90 degrees apart. Geez, I wonder if you could do one of those YMCA shifts and spot that. Okay, getting silly here. Mixture problem. Mixture problem. And I need to get a desk. I'm definitely bringing Renee the card up here the next time. All right, so let's say we go to the coffee shop and trying to stop drinking coffee, but I haven't bought any coffee in a long time, so I don't even know what it costs anymore. Word problems, coffee, 20 pounds mixture. All right, so let's say we got this length of this line segment is designated as 20 units. All right, so what happens when I take 5 units away? Well, it's not 20 units anymore, it's 15. Well, let's go back to 20 and let's take 8 units away. 8 units away. Oh, well, now the other part is 12. If that's been taken away, then that's 12. Okay, and let's find my eraser. Here it is. I didn't mean to take 12 away. I meant to take 14. Well, then I guess I have 6 left because it's 20 units long. Well, let's take X away. Yeah, I just took X away. What's left? I hope you say 20 minus X. That's the hard part of the word problem. So I got 85%. I want a certain amount at 85%. I'm going to mix with some other poundage, $1.05. So I've got 85 cents. Let's just work with 85 and remember it's cents. $1.05 is 105. All right, now I want 90 cents. I want a mixture of 90 cents. Well, that one I know, 90 times 20, right? Because I want 20 pounds. Question, how much am I selling at 85? Why do we say X? And how much am I selling at $1.05? Why don't we say 20 minus X? Equals 90 times 20. I'm not going to do that out. I just want to talk about how to get started. I have a lot of faith that we can get there from here. All right, so now we're going to look at our first derivative. And we're going to look at it from a geometric standpoint first. So I've done a little drawing. I've done some table values. I actually handed this out to you early in the term. Asked you to put it in your notebook. Hope it's still there. Don't know if you've been looking at it the whole term, but we're going to look at it now. And we're going to work with some numbers. I am going to take minus 2 times minus 2, call that 4 units of area. But I'm also going to look at minus 2.001, 3 decimal places. And you put that in a calculator, you get 4.004001. And so what's the rate of change there? Well, I can approximate the instantaneous rate of change from this. I'm changing from 0.004 to 0.000. So I've gone down 0.004 roughly. We don't care about the last 3 decimals. I could push that out 100 places. I could push this out 100 places. But I'm changing by 0.001. Does it seem believable that at -2, the area is 4 on a quadratic, and you're going down as you follow? As number x's get bigger means I'm moving to the right, which means I'm following my finger to the right, which means I'm going down then up. At 0, at -1, I get that minus, I'm not going down as fast. Oh, the tangent line has a slope of -2. That one has a slope of -4. And at 0, I get that. I'm not changing at all. It looked kind of flat there, doesn't it? And at 1, I'm going up at 2 to 1. And at 2, I'm going up at 4 to 1. And at 3, I'm going up at 6 to 1. You think you might know what you're going up at 8? I hope you're saying 8 to 1. I mean, at 4, 8 to 1. At 5, 10 to 1. 6, 12 to 1. Wow. I know something about slopes. And I know that this slope is 0, and that's the minimum value. Wow. So I wonder what would happen if I took a problem like y equals, let's keep it as simple as possible, x squared minus 6x plus 17. Wow, I wonder what the rate of change of that is. Well, it sure seems like this area here, I just go over and down, I've got a little bit more than 1. 1.002. At 4, if I just go a little higher up to 4.001 and do the area, it's kind of like layering. And now that area just got a little bit bigger, like I did 2. Like, oh, I went up by 0.001. I drew the picture 0.004. Wow. Sure looks like if I go up, let's say dx, a little difference in x, like 0.001, it sure looks like 3 times that little change, 3 times that little change is where this little change, 0.006, 001 is coming from. It's so important to see this, I'm going to blow it up. I'm going up 0.001. It could have been 0.01 to gain more accuracy, but I'm just doing 3 decimal places. Times that is 0.003. And if I do 0.001 here, well, that's times 3, 0.003, if I multiply them. And if I add those 2 things up, I get 0.00, well, I did only 3 decimal places. I get 0.006. And this is so small right there. So small, let's ignore it. Let's ignore that, 0.001. Okay, so what have I got? I've got a difference in the dimension of x here. I've got a difference in the dimension from here to here. That's that difference, right? And I'm multiplying that by, geez, what if I call it x? X, because, I think these square areas are getting bigger and bigger when I pick bigger and bigger x values. Oh, I can see increasing area. Okay, now, we can wait till you get to calculus and start talking about this, but then you got to worry about the mechanics and everything else. I think it's important that throw this in your brain right now. Is it going to be different a month from now, the conversation? I don't know. I did this to you at day 1 of the term. I showed you how to put a quadratic in graphing form, and I'm not sure there was anything going on there then, and now it seems like you own it. Let's try to make that ownership happen here in the next month or 2, because I got a lot of experience with calculus and watching students from different classes, and a lot of students don't pick it up. And that's a shame, because you can draw pictures, and if you can draw pictures, you can see things. So we'll be drawing lots of pictures. All right, so what have we done so far? And I forget what I even asked. X squared minus 6x plus 7. Let's do that. Y equals x squared minus 6x plus 7. You've done minus b over 2a, which in this case is 3. All right, you dropped it in, minus 18 cut in half, minus 9 plus 7 minus 2. And you found that is the vertex of that quadratic. Well, we just really figured out that the change in y over the change in x in these tables for x squared is a formula, 2 times x. And I know something about linear change. Linear change is, let's do a quick linear change. Let's look at y equals 2x plus 4. Okay, we should know that negative 2 gets us 0. And this is changing by 1. That goes up to 0, up to 1, up to. I think that's constant change, 2 to 1. I think we can see it from the number in front of x. I think I can see this rate of change, right? And what did we say the slope was at max and mins? We use tangent lines. And what are those slopes equal to? If you said 0, you'd be right. And so if we solve that, I think we can see that x equals negative 3. Oh, no kidding. Negative 3. Or was it positive 3? Positive 3. Yeah, that was a dumb mistake. Yeah, 2 times 3. So positive 3. Very nice. And what would this in graphing form be? It would be x minus 3 squared plus 2. And I think we just found out the most important x value. All we'd have to do is plug it back in to get 2. And I wonder what we'd get if I plugged a 0 in for x. Let's say x equals 0. Oh, I get negative 6, a slope of negative 6. And what does x equals 0 tell me? Well, that's the y-intercept. Oh, I think I've been saying that all term long. Did it without calculus originally, all right, with this notion here. But I can look at this and say, okay, I'm cup shape up. I'm on the downside, 0, 7. I now know I'm going down at 6 to 1. I know my slope is 0 there at 3. And if I drop 3 in, I get 2. And if I took the next derivative, which I'll use y double prime, positive 2, that slope, that's a constant. It's not changing. Well, I hope you can see that every time we've gone integers here, friendly numbers, our slope here was 0. At 1, it's 2. At 2, it's 4. At 4, it's 6. I think we've been going up at 2 to 1. We've been accelerating those rates of change. We've been accelerating. Okay, so what has an initial rate? Throwing the marker up. What has decelerated rate? Once gravity starts working on it. So we use quadratics to study straight line motion. All right. That's a lot. Okay, and that's enough for now. I'm sure there's some other things I want to point out, but that gets the conversation started. Tomorrow, I'll do another one, same order. I'll do them in the same order, try to simplify some aspects of recall, and we'll do it 4 days in a row. Let's see where we are 4 days from now. Yes, when you first had the first 4 days of this class, there was a lot of lost people. All right, and now we're doing, instead of 2 or 3 things right, we're doing on average around 50. That's good. Let's get 100 by the end of the semester. All right. Have a good day. Stay safe and warm. It's warming up. Spring is about to spring, or shall we say spring has sprung. All right, good enough. See you on the next video.